So excited.
And Ronald's not gonna be here?
No, that's very rude. No, I'm excited about what I'm about to teach you today.
I'm gonna leave. I decided to do this class. I'm kidding, I'm just kidding, I'm just kidding.
Okay, I can go one-on-one.
I think Ronald won't come.
What? We'll see. I don't make any promises, but today's class is the beginning of general relativity.
Oh, no.
And the beginning of general relativity is the introduction to the coolest fucking parts of physics that you've ever seen.
I did take really good notes for Rolando.
Yeah, I mean, you can watch it too.
Yeah, but it's like blurry, so I did take really good notes.
Yeah.
Oh,
Really good.
really?
Yeah, they're always like.
I tried to I get the bigger chalk and I moved the thing closer.
Well, yeah, I think you said buy a webcam. I think your camera sucks. Sorry.
They,
Well, you can say,
I even did this.
you say this is last semester that you have a bad webcam.
But I tried to plug the webcam in and it didn't work. It doesn't work
Really?
at this computer. I mean, I guess I could buy a new one. Still late.
I'll just take good notes.
You have to take really good notes.
Really
Because
good.
we're gonna go deep. Well, technically, we're gonna go broad. We're gonna talk about the whole universe today. Boring. How am I gonna fit that? I promised you, parts of this book, and that's still true. So I will get, today, when we're done with lecture, I'm gonna give this to,
Printouts.
yeah, I'm gonna get printouts and I'm gonna get PDFs for folks online so they can follow over the spring break.
Okay.
Right, so technically it's 10:30, so we're gonna start. Are there questions about anything so far? Did you have a look at homework 7? That's okay.
Sorry.
So no, that's fine. So the first 2 problems are, I noticed from the feedback that I got about homework 6, that maybe there were some things both in class and on the homework that people maybe didn't feel comfortable with. So I went back and I grabbed a couple of problems that are more like linear algebra matrix solving. And, you might look at them and be like, oh, this is super simple. Or you might look at it and be like, what the fuck is going on? So that's kind of where I want to get the feedback on, because I want to make sure that we feel comfortable manipulating arrays, solving simultaneous equations, getting transposes, getting determinants, etc. And so if you don't remember how to do those things, that's not a big deal. Just, send me a message and I can show you where to look, or I can explain it to you in hopefully clear enough detail that your memory goes, oh, okay. And then you'll have 2 problems essentially on that. There'll be something about how to do matrix multiplication, which you might say to yourself, that's super easy if I put it into Wolfram, but I really would prefer you not. That I want you to actually do the matrix multiplication so that you get in the practice of doing it properly.
I didn't even know you could put it in Wolfram, you just.
If you go, well, no, okay. No, I'll tell you because it is important for you to know. So when you go into Wolfram, there's 2 modes. There's the normal mode and there's the math mode. And so if you switch over to math mode, you can start with the matrix and you can, I forget how to, you can add lines and rows. And so you can do the matrix multiplication that way. Folks who have already looked at homework 6 saw that we rotated some tensors, right? And so we'll revisit that in the 3rd problem of homework 7, where I'll ask you to start with a 2nd order tensor of 4 dimensions. So the 4 vectors that we're used to, it's a metric, flat spacetime. So that would just be your diagonal matrix with -1 and then 1s on the diagonals. And the only difference there is that I'm asking you for a little creativity. I'm asking you to find a rotation matrix. So remember that I'm using the word rotation matrix, and that'll have very specific rules. Find a couple rotation matrices such that you rotate G, the flat spacetime metric, and you change the number of minuses and pluses. And if you can do that, There's a Nobel Prize in it.
Wait, that was probably three for homework seven.
Does that make sense? So it'll be a straightforward homework in the sense of, it's not going to address anything that we've learned today or Monday, but, you know, it will be work. And part of the work is not simply just making you do busy work, but I think because we're not so used to tensors and matrix multiplication, practice makes perfect, right? Okay. You ready?
Universe.
Well, before we get to the universe, we're gonna finish the examples that we were doing yesterday. Because we gave something yesterday, I always fucking say it, Monday. So we gave some rules about, summation conventions, right? And I'm gonna write a few more on the board. I think we did 4 last time. And we're gonna write 8 more today. And we're just gonna really see if we understand this stuff, okay? So here's the next one, okay? We're just gonna go around the room. So we don't have one person dominating the answers. So here I'll just say for people online, G prime alpha beta on the bottom, A prime alpha on the top, E prime beta on the top, G alpha beta on the bottom, A alpha on the top, B beta on the top. Valid or not valid? This one. Why?
Cause there's no free indices on either side, so that matches and sums, like everything that's summing is bottom top.
Good. So the 3 things that she just noticed, right? There's no free indices, the number of dummy indices match, and the location of the dummy indices match. That's fantastic, right? That's exactly what we want to see. So this one, good. All right, next one. Our Christopher symbol, which is 1 alpha on the top and an alpha on the bottom with beta. It's equal to 1 Christopher symbol with a beta on the top and 2 betas on the bottom. Read.
I think it
Why?
on the right, you have 3 of the same symbols. And
Are you allowed to have 3 of the same symbols?
I don't think so.
No, you're never allowed to have 3 of the same symbols, right? It's always in pairs or singles or zeros. Yeah. Okay. Good. And what else? Anything else?
That's all.
So if, for example, this on the right was gone, would this be okay?
The B is like the one previous.
Yeah, B is the only free indice. So just ignore the right hand side for a second. Is this part right? Yes, why?
Because well, the one on the gamma is gonna get summed over
The one of what?
because it has the on the side.
Yeah.
No.
The alpha on the left side.
Sorry.
Good, yeah, we just want to be clear for everyone who's following along. So alpha on the left side is gonna get summed because it's top bottom. Good, so that's why this is a good one. This one, if it was just by itself, and let's say there was gamma up here, is that okay?
But only gamma, only on.
Yeah.
Yeah.
No, why not?
You said the rule yesterday that it has to be top bottom.
Wait, okay, so you mean,
So let's say I change this, right? If I do something like this,
oh, no, it's above the bottom.
exactly right, okay? All right, so that's the other rule that we want to make sure that we pay attention to. So not only is there too many symbols over here, they're coupled on the bottom. Good. Okay, good, that we crushed those two. Sarah, do you feel comfortable jumping in here, or you want me to just go back and forth between them?
I just
don't-
sent her the rules.
I don't feel comfortable, but let's try it.
Let's fucking go! Yeah, that's the energy I wanna see on a Wednesday. Alright, G alpha beta on the bottom. A alpha on the top. B beta on the top. Equals G beta on the bottom gamma. A beta on the top. B gamma. No helpsies here, no helpsies, no faces. No secret knowledge.
Based on this.
Oh,
So it says that the Greek letters are 4 vector spaces,
Mhm.
and that. Would that be no, because they're not technically equal, because gamma's a different one than alpha? Or would it be yes, because it looks like this rule 3 where the 3 indices have, no, it says 4 indices have to be the same, so no, it's not.
So on the same side, they have to be the same, that's definitely the truth.
Okay, okay.
Because this is an equal statement, we can use, as long as they're not free, right, if they're in pairs, pair and pair, pair and pair, those are considered dummy. So the dummy ones can be whatever we want them to be. Because what we're asking is that on this side, they will be equal to this side,
Okay.
right? So for example, beta and alpha now would have to take the same values, and beta and gamma on these would have to take the same values. But in these sums, we don't necessarily care that there's betas over here, unless there was another symbol over here, like a delta or something else, that I'd have to match the two sides because they're free. Does that make sense? Okay.
It's kind of suck, I can go through them with you after class.
It's okay.
No, she's gonna get it. Watch.
I took bad notes.
Watch,
I
watch,
think
watch.
I took bad notes.
Okay, all right, well, we'll see.
I don't
All right,
know.
next one. We have a Christopher symbol. Alpha on the top, alpha on the bottom with gamma. We have A with gamma on the top. That's gonna be equal to G alpha beta on the bottom. A alpha, B beta on the top. Isabel?
That's a weird.
Whoa, that's a weird one. Let's ask another question too, just to remind ourselves. What's this thing?
Those were, one of them's coordinates, one of them's, the bottom's vector, the top is coordinates.
Good.
So I don't know how the cursive thing works, but as long as the A is just telling you the coordinates, that's fine, but I don't know if that's allowed or not, because I don't know how that works.
Okay, well, just thinking about this in the context of what we know, right? We don't know how this thing works or what it means. But we do know that it has 3 indices, so therefore is what? What kind of tensor? Third rank. Good. And so if I see a repeated index here, what does that mean?
Summing over,
Good. So if I have a repeated index, and let's imagine that none of this was here, and I have some repeated index, so I only have one, what would be a free index, this would essentially be what type of object? Once the sum is done,
a bunch of scalars, or like a vector of numbers multiplied.
right? Because I only have one index, it would be a vector.
Yeah.
Right? So the way that you should look at this, when you see a repeated sum inside of a single object, if you have the dummy indices and they're the same, then you can think, oh, that's really gonna end up as a vector with gamma on the bottom.
So it's just, will that end up as a vector, that is the question?
Yeah, so the question is, so let's look at all the indices. These match. Is that gonna sum okay?
Yeah,
Is this gonna sum okay?
Yeah.
So this would be a vector times a vector. And this would be, the left-hand side is a scalar.
trying to think if the GA would make a vector.
Well, the GA makes what? This G alpha beta is a second order, and we know that G alpha beta is our definition of a metric. So we say here, the metric for flat spacetime, Cartesian,
How am I supposed to memorize letters anymore?
I know. I'm just gonna show you an example. We're not memorizing letters, but I'm telling you that the metric for a flat Cartesian coordinate system is what?
It's like, oh, flat is -1, 1, 1, 1, 1, plus negative zeros.
Good. So we're gonna we're gonna see that, and that's what we're gonna think. And maybe it won't say G. Maybe it'll say something else, L, bottom. But if it has those two values on the bottom, then we know that we're describing coordinate spaces here, right? Such that you end up with something, when you multiply it by your vectors, you get a scalar. Well, look at this, right? This one here, these are gonna sum.
Yeah.
And these ones here,
So,
these are gonna sum. So on the right hand side, it's a scalar. It has to be a scalar because there's no free index.
it's,
Yeah, so here
Oh.
they matched, here they matched, here they matched, here they matched.
yeah, but the GA is a vector.
Oh, yeah,
That's
sorry.
what it's-
Oh, not a vector, a tensor.
Just the GA together.
Right, just the GA together is that. Right, a second order tensor. Or what we would call a matrix.
No, like, just cover the B.
Oh, like this,
No, the B, not the beta.
like this.
Yeah, that's a vector.
Ah, yes, that would be a vector.
Okay.
Yeah.
So that's fine.
Good. People agree? Still with us? It's okay to say no, it's okay to say slow down, come on. All right. Reed, you ready? Let's get real in here. All right, so now we're gonna do the next one. We have del XA. Oops. Not an A. Del X fish. Del X beta. Equals delta alpha beta. What do you think? You think it's okay? Why? Well, which one is it?
Cause the thing on the right,
Mhm.
those don't like get summed up together
Why don't they get summed up together?
because they're different indices, so they're not gonna sum.
Okay,
I know that said that previously, you could have the stuff on the left equal, constant, that's okay, but if this is not like a scalar value.
yeah, this is a chronic for delta, right?
Yeah.
So what does that look like?
You know, what are you gonna put this in for?
You tell me, I don't work here.
Well, it has the same two indices, they're in different places,
Sure,
but it's the same thing.
sure.
We can bring the other one down.
But that's gonna cost us, right? That's gonna cost us a minus sign.
Yeah, but.
So let's just write what it is.
Alright, well, I'm not sure what it is.
Okay. What about a normal chronic or delta?
Well, it's either one or zero.
Good. And where is it 1 and where is it 0?
I'm gonna guess it's a one along diagonal and then zero.
What? Why is it 4?
Oh, Greek letters, sorry.
Greek letters. So that was a secret rule that says anytime we see Greek letters as indices, we use 4 components. As opposed to our good old friend delta ij, which is
Three. Okay.
a minimum or a maximum of 3 by 3, right? Okay,
Which one's the indices?
so from now on, we're not seeing subscripts. We're not seeing powers unless we're gonna do, like, if I wanted to square this, I would do this. We're not just gonna do that. Does that make sense?
It's like a for loop, it's like for I and it's like the beta and the alpha are like. the
Yeah,
alpha.
what we're gonna do is we're gonna try and do this convention in a way that is self-consistent, so like I won't use powers that are not Greek letters. So let's say it was something like a to the x. Right? That would be a power of a. As opposed to if this was a vector that I'm summing, you might have something like that. Although that's a little gross, I probably would do that. Does that make sense? Just to clarify it.
A little.
And I'll try to be as good as possible, but you know, everyone's allowed to make one mistake in their whole life. So, I already did it. Okay, so the right-hand side you like or no? Well, I wrote a version of, I mean, yeah, you're right, it could be anything we want, right? Remember that we're ignoring letters and numbers, but in this specific example, I know what this one is, right?
It makes me uncomfortable to see it, part of your grammar delta with the thing on top, instead of on the bottom.
Okay,
Yeah.
yeah, that's fair. I'll let Hartle know about it,
Okay,
if it's still alive. He's at UCSB, we could go see him.
yeah, I was like, hey.
Knock, 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 hello. Okay, so let's imagine that we're, okay, weird, it's weird looking, it makes us feel strange, but we're gonna get over it. Right, and this part we think are okay with? What about this one? Okay, why do you think it's fine?
Um. The indices are gonna stay, like, no freaks on the right, they're not, the indices aren't gonna get summed over,
Good,
so they'll stay the same for the left.
Good.
On both sides.
so the number of free indices is matching AA and BB. There isn't a sum between top and bottom, good. You should feel uncomfortable here because the B is not on the bottom. But we remember that there's a secret rule. Okay, that anytime there is a derivative. Such as, so this is a secret rule. Because this is fucking hard to do. We say something like d x a. Sorry, I'm saying a, I don't mean a. Dx alpha is equal to the partial x prime beta x alpha times d x prime beta. This one here acts as subscript. Okay. So anytime you see an up, sorry, a superscript in the denominator of a product, sorry, of a derivative, that really means it's on the bottom. So you are right that this one's okay, but we have to quote this secret rule, which is a sub rule of,
What if it's just right on the bottom?
you know. I don't know, I don't make the rules, I just tell you what the rules are. You know, if I had come up with general relativity, maybe we would have done things a little different, right? That's 100 years old.
Yeah.
Maybe not quite, something.
I don't know if you did in 1942. Might have been more.
And the special relativity was in the 1910s. So I have to figure that out. I'll go. Okay, Next one, this one's a real doozy. There you go.
Yeah.
Okay, G alpha beta. The partial of X alpha with respect to the partial of X prime gamma times the partial of X beta over the partial of X prime delta, not that delta, equals G gamma delta partial X prime alpha X gamma partial X delta partial X prime beta. A lot of words.
So with the G alpha beta. If the thing like the gamma and the delta aren't part of that, that makes it free variables.
Say that again, so if the,
So G alpha beta on.
Here.
And then you have gamma and delta. Are those considered?
Here?
Yes, are those
Good.
considered free variables?
right, so you notice that the alphas are here, they're matched. And the betas here are matched, so alpha and beta on this side are dummy. And the gamma and delta are free.
And then it would be this, the opposite on that one. I don't know if free variable rule. Free
Good.
indices have to
Yeah,
be the
so this
same.
is exactly correct.
Yeah.
Right,
Yeah. Rule 3 says free indices have to be the same,
right,
and they're not.
so this is wrong. Good,
How do you keep track of all those letters? Or,
yeah, it's a nightmare, but this is why we have to, this is why we're doing all of them, right, so we can practice. Right, so we look at the G's, we see the alphas on the bottom, once they're up here, you're like, oh shit. So let's say you're writing this, and this is your work, you'd be like, oh wait, they don't match, let me switch. Right, so that the free variables do match, or the three,
three is actually two batch.
no, they don't.
There's that one, and those two are free, and that one, and the bottom two are free on the other side.
Well, there are the same number of free, but they need to be the same free,
Oh.
right? So you're right, you're right, no, on this right-hand side, right, we could choose any other, like this, this. This gamma and this delta could be like mu nu. And this could be mu nu, but these ones here are the ones that are giving us the issue. Because this needs to match this, and this needs to match this, or vice versa. Right? It's not simply the number of free indices, it's that the indices themselves are the same. Okay, cool? All right. We're making good progress. We only have two more. You ready?
Uh-huh.
Okay. A alpha times G beta gamma on the bottom, B beta on the top, B gamma on the top equals B gamma on the top. What? Why are you laughing about?
So I guess no, because the three indices don't match.
Correct. Did the number of free indices match?
Yeah.
Yes. So the thing inside the parentheses is what?
A scalar.
Very good. And are you just like seeing that now, or does it take you a little while to?
I think maybe no.
That's okay, yeah, no, I'm just asking, right, because I think with more experience, you'll see repeated indices. And you'll be like, oh, that knocks this product down to a blank. Right? Because if this one wasn't here, right, what does the thing inside the parentheses become?
Vector.
Go back to it. And you'll get more practice seeing it. Okay. Another reason why we're doing all of this, especially with the tensors, is because we're representing sometimes, 16 equations with one line. Right? So, if you have a 4x4 matrix, you have two 4x4 matrices multiplying each other. That's a 16x16 matrix, right? Okay, last one. Read, you ready? Close it out. It's the hardest one. You want to do more? We're gonna do more.
No,
Go back to the beginning.
no.
All right. Read got lucky. What?
Thanks, I got it on my cousin a few years ago.
All right, Reed, what do you think?
It's, things wrong,
Why?
because I think that DNC.
Interesting. Is that a rule?
Well, the
Which
letter-
rule? I mean, you have the rules in front of you, right? Which rule is true? I like when Sarah's like, according to rule 3, index 2, this is invalid under section 3.2 of the code.
Feel weird.
Yeah, it's great. No, I mean, this is the way that we do the math, right? You're like, does this fucking work or not? Ah, okay, good. So what are the rules? Let's be specific, right? Let's make sure that everyone's learning as much as we are. So what is the rule specifically that you're referencing?
The third,
The third rule, which says?
which just says that. The things. But the swap. So, the things.
Sorry, just break that down a little bit for me. Sorry, so
Yeah,
this indice is matching this one.
yeah, and if you swap the places of where the free indices are, it's the.
Okay, so just to clarify, because I want to separate two things happening right now. If I have G alpha beta and I have G beta alpha, they're not necessarily equal. Right? Because they're matrices. If I swap the position and let's say it's not a symmetric matrix, I may have fucked everything up, right? But in the example that I gave, this was okay, right? This isn't always true. This is okay to be true, right? This would be a requirement. Let's say these are the same matrix. The statement G alpha beta is equal to G beta alpha is a statement of symmetry, right? Which is only true in symmetric matrices that already exist. But is not always necessarily true, right? So if mu and G are the same, then both mu and G are identical and symmetric. But if they're different, then flipping the indices here, right? So then G alpha beta is basically the transpose, or mu is the transpose of G alpha beta. Do you see that? Okay. So matching them up there is important. We see the same number of free indices. We see the same number of, or they're on the same bottom is what I was trying to say, right? You don't have a beta on the bottom and an alpha on the top. And we can say something interesting about them if we understand a little bit about what's inside of them. Okay? Is that what you meant?
So they're only equal if they're merged.
The summation notation is fine, but it's only true if it's true.
Yeah.
Wait, wait, now you're confusing me. Okay, so this statement is a separate statement. So at the end of rule 3, I said something like this, right?
We have to clarify that they're symmetric.
Like you can't say that things that aren't true are true, but the notation is fine.
Well, so hold on. So G is the same thing, right? So this is the statement that is true because G is symmetric.
Right.
So this is perfectly fine, right? This is a valid statement from the context of our rules.
Is that okay? Because they
Yeah.
have different lengths G and the letter okay, as long as they're the same matrix?
Well, no, we don't know what this matrix is.
But can you, is that okay?
This is okay because we don't know what that is.
Cool.
Yeah.
Wait, but
Does that make sense?
no, if you don't know what it is, we don't know if it's big, we don't know if it's thing.
Well, let's imagine that I hand you G. Okay, here's G. And you say to me, okay, well, now that tells me something about mu or eta or whatever this is. right? This left-hand side, just like if I said, x equals 4, I'm giving you information here that you use to figure out mu, or vice versa.
And instead of it being symmetric, you're saying it can also be like this mu, right, or mu?
Yeah, let's call it mu.
Mu,
I know it's not.
mu could be the transpose of G?
Right, that would be a way that I would interpret that. Right, let's say that this is not a symmetric matrix, that this is just a bunch of numbers in a bunch of different locations. The way that this would be true is if G were the transpose of eta,
Or vice versa.
or vice versa, because the transpose simply acts to change the ordering of alpha and beta. So therefore, it would identically be true, right? I know that that feels abstract, but the more that we play with it, the more that it makes sense. I think, hopefully, we'll see. Okay. How much? Okay, here, here.
I just don't like.
All right, welcome to the club. Okay, is that good? So that's like 30 minutes of remembering how to use all this stuff. And now let's see why we want to use it at all.
Universe.
Okay, so Reed, you missed this at the beginning, but I was gonna say that this is the best part of all of the classes that you probably will ever take. And I'm saying that just because I'm giving the class, obviously, right? So, no prejudice in my opinion. So, my motivation for teaching you tensors is because I'm legally required to in this class. My interest in teaching you tensors is because we can use them to understand general relativity. And general relativity is okay. So what are we gonna say here? We talked at the very beginning about this idea for special relativity, that there is no special frames. That someone moving on a train is gonna see the same physics as long as they're moving at constant velocity to someone who is standing, watching the train going by. So you throw a ball up on the train moving at constant velocity, and you throw a ball on the ground, and it'll look the same. Ball's gonna go up, ball's gonna go down, and neither of you can tell who's moving. Right, that's the idea of the local equivalence principle. Local meaning where you are. Okay, so physics should look the same. That's a requirement. Okay, we can generalize this equivalence principle. I don't know if I need to write it down, but essentially, we go up into space. We realize that we're on a big ball. That ball is heavy and it pulls us. So we are rotating right now and we're flying through space, we're hurtling through space, and yet we make all of these statements about physics being the same and all of these different coordinate systems. Where did I just highlight this box? I did. Oh God, this is why I need more tabs. Am I going crazy? Am I going crazy?
Well, no, you can do something. You send them to the.
Yeah, and I'll send Rolando also we'll get the PDF up. Okay. So here's the equivalence principle. Experiments. In a sufficiently small, really falling lab over a sufficiently short time is identical results those in an inertial okay. What does that mean, good money?
Falling plane. Is it a lab where you're dropping stuff or is the lab itself falling?
The whole lab is falling. Okay, so we go to the Empire State Building. Okay, we take it up to the, I forget how high it goes. It's like pretty tall. Okay. And we get in the elevator. Okay. And we cut the cable. And we start falling.
The great lab.
It's a great lab. Okay, so now we're in free fall. Okay. So now what happens here? So are we experiencing gravity locally?
Yeah.
Yeah, we are. We're definitely still within a gravitational potential well. And in fact, we're undergoing acceleration, right? However, everything around us will just stay where it is, right? Or if I have a ball in my hand and I now move my hand out of the way, what does the ball do? Okay, so I have this, let's say I have chalk in my hand in my lab.
Yeah.
Okay, I'm in an elevator that's now falling. If I move my hand out of the way, what happens to the chalk?
It's
They get
floating in the
close.
same spot.
Exactly right.
I've been on Tower of Terror.
Yeah, you get to the top and you see the ball floating, right? Okay. Okay, so experiments in a sufficiently small, freely falling lab over a short time scale will look like those in an inertial frame. Okay? Now in this inertial frame, we don't have gravity. Okay? So it's the same. Like in, I should clarify this statement. I didn't write the very most important thing here. In MP space. Oops, invert modifier.
As opposed to like hitting things.
Well, so, you know, if you think about Galileo's first thought experiments, he said things like, there is this object called inertia. Objects in motion remain in motion. But that's never been true in nature on Earth. He never once saw it happen. So he had to imagine if you're out in cosmos, away from anything that might give it a force, an object in motion will remain in motion. And an object at rest will remain at rest. Right? So therefore, you can achieve the idea of inertia in a freely floating elevator. You move your hand, and the object stays there, right? Because there was no force acting on it. Yeah. Don't think about it too hard. Remember, it's small, freely falling, short time scale.
Or just the area around it is experiencing the same force.
Yes, this is the idea of the equivalence principle. And what we're going to do is we're going to talk about moving from a local frame of reference to what you call a causal frame of reference. That is one that encompasses the whole world or universe, so to speak. Okay. And in particular, let's say we're in this elevator and chalk's like this, right? And I flick it, right? What does it do? So yeah, it just keeps going, right? And if it was a long enough elevator,
It would go until it's small.
exactly, right? So the rules look like an inertial frame in empty space, right? Now you have to flick it hard enough that it keeps going until it hits the thing before you hit the floor, right? But we said short time scales. Okay, this is the generalized equivalence principle, okay? And this will allow us to do physics in curved spacetimes. Okay, and you know, I talked myself into a trap when I said that no one had ever asked about what flat meant. So let's actually describe what flat means in the context of math. When we think about the local inertial frame, we are going to say a couple different things. We're going to have some metric, G prime, alpha beta, at some transformed coordinate like this, which is going to be equal to eta alpha beta. Okay, first, is this an okay thing to write? Why?
P?
Yeah, P is not a Greek character.
But the free indices so much,
Do they?
is free and the rest are. Oh,
P can never be a free index because it's not.
okay, sure.
Yeah, so this is just the way that we're gonna, so what I'm saying is X at a point P. So what I'm trying to describe here is that we can find some metric that we can transform into a new coordinate system. Okay, and then we can describe the coordinate system therein. Okay, this one here, we're gonna reserve this. This is the flat spacetime metric. Part. Okay, so that little eta you might think of, or the M, you can imagine that's an M for the Minkowski metric, right? Flat spacetime. Okay. So you can, and you'll see in this homework, I'll ask you to rotate the flat spacetime metric to change the distributions of positives and negatives, to turn time-like coordinates into space-like coordinates, and so on and so forth. We saw, excuse me, we saw that the, oh my goodness, sorry. We saw that in the middle of Monday's lecture. I tricked you, right? I made like dt into something that was associated with a positive component, and dx was associated with a negative component, right? Whereas what we're really supposed to think of is the different parts of the metric. The positive parts are associated with what type of value? Space-like values. And the negative parts are contributing to temporal components, right? Good. Okay. So I'll let you work through the implications of that in the homework, right? Trying to rotate the flat spacetime metric to change if you can make more time-like parameters. But you will find, hopefully, unless you come up with brand new physics, you will find that there is only 3 dimensions in space and 1 in time. Hopefully. Otherwise, we're gonna make lots of money, okay? All right. So how much further can you go? It's not possible generally to find G alpha beta equals the Minkowski metric alpha beta over all curved space. Okay, so now let me read that back, now that we understand what a few of these words are. First of all, read, is this okay? With the condition, right? Good. So what this is really saying is this is a comparison of 2 second-order tensors. And we, as general relativity experts, now know that this on the right-hand side is the Minkowski flat spacetime metric for 3D coordinates. Whereas this could be any metric. G is just a generalized metric of any type. So what I'm trying to say here, this is not necessarily always true, particularly over all curved space.
The way you're writing there, you just, sorry, you're saying that it's only true at some points, but not that it's untrue everywhere?
Exactly right. So in fact, what I'm going to try and show you today is that some flat spaces will exist locally, but that generally speaking, you can be in a curved space. So I will say something along the lines of, you can find, right, you can generally find this statement, okay? We said this, we're gonna add this one here. This is G prime alpha beta over GX prime gamma, okay? First of all, does that look okay before I continue? What am I saying? Fucking knows, bro. Shut up, Chris Money. Teach the damn class instead of testing us.
If the, sorry, gamma, alpha, gamma?
Yep.
If the gamma's on the top and it's actually on the bottom,
Mhm.
does the other ones have to be on the top or is it okay?
But we're not summing over any of them, right?
Oh, never mind.
So we're not worried about that. So this one looks okay. What does it mean? What is the operation that I'm doing to the metric? Differentiating, right? Good.
You see how it's changing at different points? Is X space?
Well, X is not space. X is,
X
no, X is,
point?
no, X is. Almost there, almost there.
If it's a Greek letter, it means that it's blue.
Space set?
Space-time. So X is space-time,
So how it's changing over space time?
right? So what does this really say? This says, what's the slope of the metric in space-time? Okay, so now let me finish this statement. I'm gonna evaluate this at X equals XP. Okay? And in order for this to be flat, what do I need this to be equal to?
U thing?
Easier.
0?
Correct. Okay? That's the intuition for general relativity that I'm looking for, right? What does it mean by flat? The derivative is 0. It sounds stupid, it sounds simple, but this has enormous implications, right? So if we can find a metric that's evaluated at XP where the derivative is 0, then that is locally flat. So these two items here are the requirements for local inertial frames. C'est bon? Good. That's not even that complicated, right? And now you totally understand what it means because you love all these little Greek letters. And they're super easy to use, right? No one's freaking out. Okay. Yes or no? No one freaking out? Want to see an example? Okay. Let's do the simple example first, and then we'll do the one that's gonna maybe hurt our brain a little bit. Let's imagine that we lived on a giant sphere. Okay? And let's imagine that that sphere was so big that when you're on the surface of the sphere, you look in all directions and it looks flat. And there's just like groups of people who argue about this with you constantly. They're like, oh my God, the space-time that we live in is completely flat. And you're like, no, it's fucking curved, bro. Like it's a curvature that is, non-zero. And they're like, no, man. Okay, the local space-time is completely zero. Look in every direction, right? So that's the argument that we're gonna have. Okay. I'm having fun. You might not be having fun. Okay. So let's imagine, if we will, we want to build a space-time that exists in this reference frame. I want to know the geometry of a sphere. Okay. So let's write this down. Okay. Just looking not at time, just the space component first. Let's do the metric of a sphere at the North Pole. A sphere at the North Pole. A sphere at the North Pole. The elements of ds squared.
Is it gonna be similar to spherical coordinates?
Yeah, probably, right?
Great.
A squared. Phi squared. Plus.
Spherical, isn't it?
Yeah, we're gonna say that the A is the radius here.
Each one looks like we have to ignore letters, and just accept that they could be random letters now, not just like R for radius.
I know, but it's how that's wild. It's not even mess it up.
What?
You can mess her up for,
Yeah.
Oh, E&M's not even a real class.
Why are they added? Not multiplied.
Which?
Square root of
It is a squared times d theta, so it's r squared times d theta.
So it was like if you're doing square root for this is r squared sine theta squared d theta d phi. And they're all multiplied together.
So each one of the X, Y, Z components is gonna have something different.
Oh, yes, of course. I
That,
take
that might, there's also the area, this is the length.
Right. And we'll see volumes and lengths in spherical coordinates soon. But the important thing here is that you'll notice there's no dr squared. Why is that?
Because you're at the North Pole. And
Oh, the radius. Here's square.
Yeah, right, so we're just assuming the radius of the Earth is what the radius of the Earth is. And you are not gonna make a sizable contribution going up or down. Maybe you jump up, right, but I know, but you know, you're not 6,500 kilometers good at jumping. Okay, so we're gonna imagine that we're stuck to the surface of this sphere, right? At the North Pole, theta equals 0. So that might be your question, right? So you get close to it, and we're gonna look at these. Let's write a couple more things here. The metric doesn't really look like a flat plane. We would agree that this is the metric for a flat plane.
I thought flat didn't mean Cartesian.
Generally flat, right, mean this,
Yeah,
but we did show that the Cartesian was flat.
but you can also have flat space-time and spherical.
Well, the coordinate system you can transform from spherical, sorry, let me say this differently. The space-time metric itself is flat for Cartesian coordinates. Right? The question is, if you're on a sphere, if you're on the surface of a sphere, and you're only allowed to move on the surface of a sphere, does it look curved or does it look flat? You see the question?
Yeah. Yeah.
Okay. Okay, let me show you. Okay. So so the first derivatives of this metric, do they vanish? Okay, let me ask you this question. Here's G, I'll do IJ here for 2D metric. For the flat plane, what is that? Good, and we only have 2 dimensions here, so it's like this, right?
Yeah.
Okay, and so now let me ask you a question. Can I take the derivative here with respect to X and Y? And what am I gonna get? The derivatives at each location. Yeah, right, so let's imagine this. I'm gonna do G, all right, let's do it like this. I'm gonna apply that to each one of the individuals, right? So it's gonna be 0, 0, 0, 0. So that's the definition of flat. Right? What about the one on top?
They would also be flat.
Oh, we don't know yet. We don't know yet. Right? I said
Oh.
this one was the description for someone who's stuck on a sphere.
I guess it's sine.
And I said this one is the definition for 2D Cartesian space, right?
I thought you said during the other class that just because you're using spherical coordinates doesn't mean the space-time is flat.
Right, but hold on, so the difference here is I did not take this and transform it into this. right? That would be a
So it's a different
transformation.
Space-time.
Yeah, I gave you this space-time,
You wanna figure out whether or not this space-time you gave us is flat.
correct?
Okay, but just because you're in spherical coordinates doesn't mean it's not flat.
Exactly.
Okay,
Right. So if we had done what we did on Monday, which is to start in flat space and transform it into Cartesian, or sorry, spherical coordinates, then you would maintain the flatness. But if I create a metric that looks like this, the question is it flat? Okay. All right, so let's consider the following coordinate transformation. I'm gonna delete a little bit of this, if that's okay, just to make it a little clearer, so I didn't give myself enough room. Is that okay?
Yeah.
If we write something along the lines of, X, we're gonna define as A theta equals phi. And Y, we're gonna define A theta sine phi. This is gonna give us a transformation that looks like theta square root of x squared plus y squared all over A. Whereas phi is just gonna be tan inverse 1 y divided by x. Okay, that's a little simple compared to what we think of as transforming between two coordinates, right? Reasonably or not? Yes or no? So let me ask you a question here. This ds squared, we can grab those components and we can turn them into our, G, A, B, or G alpha beta, however you want to call it. So let's put this into there where we see it. Okay, we're going to transform this into powers of x's. Okay. So generally speaking, you're gonna have something that looks like this, G, and I'm gonna use A, B here because it's not four-dimensional. Is that okay? And this refers to X and Y here. This is gonna be a 2 by 2, and it looks like 1 minus 2y squared over 3a squared. And it'll be the similar thing down here, 1 minus, minus 2x squared over 3a squared. And then up here, it's 2xy for 3a squared. Down here, same thing, 2xy for 3 squared plus terms in x, y. So now the question is, at the North Pole where we started our origin, what is x and y?
is that 0, 0?
Yeah, that's 0, 0. Good, and what is our space-time metric look like? Or sorry, I should be more specific. What does our space metric look like?
At 0, 0?
Yeah.
I guess it would become 1, 0, 0, 1,
Which is?
flat.
Good. Right? Okay. And you could take the derivatives of that flat and it would remain flat, right? Because it's 1, 1. And what happens if you move farther away from the origin? Let's say y is like comparable to a. Maybe half of a.
Well, you'll still just get numbers. And if you took the derivative of just a number, you can still get 0.
Well, okay,
You won't have a variable in it if you're plugging in.
right, yeah, that's true. So locally, you evaluate it at a point, right, depending on how you move the coordinates, it's don't always look flat. But if we think about it in the context of, remember that we said that GAB is what we use in order to find the distance between 2 points? In space or space-time, right? Take a vector, another vector, and in order to find out how far away they are from one another, we multiply them together with GAB or G alpha beta, depending on if it's 4-dimensional. Remember this part?
No, I just remember G as the thing you use to like keep everything you need to make the coordinate system.
Right, yeah, so think about it in the context of ds squared. When we want to know something is time-like separated, space-like separated, or null separated, right? Don't we have each one of those different components added and multiplied together?
Yeah.
Yeah, and the first one always gets that negative sign. And that's from the metric, that's not from the vector itself, because the vector itself doesn't know that it's negative, because if it was 2 negatives, they'd multiply each other and they'd be positive. So it's the metric that lends the fact that the temporal component is negative, right? Okay. Does that make sense? So. What?
Okay, but
Okay, so let's remember when we do the derivatives here. Right, Isabel? So you were saying, well, if you evaluate it at a point, the derivatives will always just be numbers. But we take the derivatives first to find out if it's flat or not,
Before you put in the numbers.
right? Because then you evaluate it at x equals a large time distance away. So let's ask the first one here, okay? dx for this first one,
The X.
Yeah.
Z.
0, good. There's no x's in here, garbage. This one,
Everything except for the X.
yeah, non-zero. Okay, so if I move far enough away, right, and I evaluate it, what do I get?
Maybe you move like. in
Okay,
X.
I'm at 0. Okay, here, even if I took the derivative, if I'm at the origin, this is still gonna disappear, no?
So the farther you go in Y, I think that derivative is bigger the number.
Right, yeah, the more unflat like it is. Because we asked for them all to be 0. And there's curvature. Right? Yes or no? You can say that this doesn't make sense. I just want to see if we're getting it, because what I'm trying to do here is I'm trying to show you that this choice of a metric is a curved metric. This is not flat space. And therefore it has implications. It can look flat locally, right? You can evaluate it at the origin and the non-flatness disappears. But as you move far enough away, just like we know on Earth, you have to consider the fact that you're attached to a curved object, even though it feels locally flat. Is that okay? Okay, and in particular, we use this when we go on flights, right? Why is it that when we look at a plane that goes from here to here, the plane doesn't go like that, it goes like this, right? The plane flight, if this is Miami, or this is Miami, and this is Seattle, okay? The flight doesn't go straight. The flight goes up and around. That is the shortest path on a curved object. Right? And guess what? The flight companies, they want to minimize gs squared, because that means less gasoline, or whatever they use, jet fuel, right? So this is the idea of us being locally flat, transforming and using the metric on a curved object. This will be the easiest one we do. We'll find cooler ones. I really wanted to get to warp drives today, but I think I'm only going to be able to introduce you to the idea, and we won't be able to work through the ramifications until after spring break. Okay, so it is not possible to find a coordinate system that makes all of the second derivatives of a curved surface of a curved metric, I should say, equal to 0. Why is that? Well, that's kind of maybe a dumb way to say it, because if the second derivatives of that curved surface were 0 everywhere, then of course it would have been not curved in the first place, right? Okay. We were just talking about time-like and space-like and things like this. So let's draw one more fun picture, and we won't get to warp drives today at all. We said something along the lines of ds squared in 4 space represents separations. So in general, I want to say something that's more fundamental really quickly. So we're going to say something like ds squared is less than 0. What does that mean? Nope. This just generally for a 4-dimensional.
Timeline?
That's time. Good. And who travels on time-like paths?
Yes, say astronauts.
Yes, yeah, astronauts do. Who else?
Really fast people.
Not necessarily. I traveled on a time-like path to get here. That is traveling on a time-like path. I'm pointing to the station. What does time-like mean again? Well,
Oh,
it just is looking at, this is ds squared. Or are you staring at it? Okay, let's remember what the metric for flat space-time looks like. You have 3 components which are positive and 1 component which is negative. So in a flat space-time like this, x this way and time this way, you have light cones. This here represents the null. So this is d s squared equals 0. And who gets to travel along those light cones? Light. Good. Good. So this is d s squared equal to 0. This is light. And only light for mass less particles and travel. Okay. Time-like goes where? The time-like ds squared is less than 1. That means that the dt component of your motion is larger than the amount you move. And we have to remember that we've hidden a value of c in here, because it's c times t. Right? So here is Krismani's path to work.
I don't want to now confuse that, like,
What? No, I didn't get very far. This compared to how long it took me to get there.
traffic?
Well, wasn't moving the speed of light,
Oh,
right? Okay, and at every point, we can imagine that there is a light cone. And this side here is the future. And this side here is the past. Right? So this is the past. This is the future. Now I can only get so far within my personal light cone because I can't move faster than the speed of light. So I can traverse any of these locations, right? As long as I wait long enough to get there, depending on how fast I am. And the last one, ds squared greater than 0, this is space light. Who gets to do this?
space.
Yeah. Nothing with mass, nothing with energy gets to do this. Well, let's talk about it. Okay, so one thing that I drew here that I didn't highlight, okay, when someone wants to describe their day in the context of one of these light cones, etc. Okay, this is called a world line. The world line represents all the paths that you did take. So you might have started down here, and then here, and then gone off, and then back here, and then back here. This would be your world. Now, did they know that they were going to be talking about the universe when they created this? Should this have been called the universe line? It has absolutely a better meaning, but we're stuck. Okay. So what is the what's the type of world line this is? It has to be time, right? Because it exists within the time cone and it never goes faster than the speed of light locally, right? What about this one here? Light, wow, light did light, okay? Cool. All right, so that's really important. You can integrate over any time period to find the proper time along one of these. I just want to show you something. I'm sure I better draw it. All right. So we can make a coordinate transformation, and we're not going to be able to get into this today. This is just going to help my odds. Okay, so this is going to be time in a new coordinate system that we'll talk about in 2 seconds, and that'll be space. And I want you to see that these are going to be basically what we form our cones. These are our light cones at a specific point. Okay. And as we go over, we see that they kind of widen. Okay. So this is a light cone over here. You can enter through the bottom to get to this point, and then you can exit to the top. Right? And you might have something like a trajectory that starts you out over here. Okay. See if I can draw this properly. Fucking up too badly. Here. We're going to cross multiple world lines. Okay, we're gonna try it anyways. We're gonna start outside of this one. We're gonna go through this point. Okay. So here's a big wide one. We came in. And then it narrowed up. Okay. And then we went through, well, that one was not perfect. This is supposed to be a cone here. And it looks like I got pretty close to the speed of light. It's not exactly perfectly drawn. And then I headed back out. So the cone may have started really wide, and then it shortened up near the origin, and then it got wide again. What we're describing, at every point along my world path, I can describe locally the geometry of the metric that I'm in and build a light cone of my future and my past. And because I'm moving on a time-like world line, I know that I need to be inside of that cone. I can't be on the edge. So this was a no-no for Prismani. Very bad. Give me my money back for today's lecture. Does that make sense? And where I want to go, what I want to show you is how we can bend space-time itself such that we can turn the light cones on their side so that locally we are going below the speed of light, but when seen from outside on a large scale, you will appear to be moving faster than the speed of light. This is the idea of a warp drive, and it's possible with general relativity. The math is possible, but realistically, it'll never happen. We'll also talk about what it means to have a wormhole, what it means to have a black hole, etc. Okay. Sorry that I didn't get far enough, but this is like, you're about to get into the shit right now, and it's very cool.
Your outro?
Yeah, I need an outro music. No one watches these